Now this is a Wi-Fi jammer, meaning if I bring it close to my laptop whose internet connection worked just fine, then it immediately loses that connection. And no, this is not illegal, because it only works up to a distance of around 40 centimeters. This jammer works by spewing out electromagnetic waves that come with around the same frequency your Wi-Fi utilizes. And needless to say, such unwanted electromagnetic waves are not only annoying for my Wi-Fi network, but they can also influence the functionality of basically any electronic circuit. This all ties into EMC, aka electromagnetic compatibility. And in the last episode of my EMC adventure, I took some of my homemade buck boost converters that can step up or down a variable input voltage to a stable output voltage and got them tested in a proper EMC chamber. The results were pretty clear, telling us that they all radiate too many electromagnetic waves, and thus they failed the tests. Now back then I ended the video by saying that there are 3 solutions to this problem. But recently, while taking apart an old hard drive, I noticed a 4th solution we forgot about: shielding. And believe it or not, but shielding is all around us when it comes to electronics, and oftentimes overlooked. So in this video, let me show you what shielding techniques are out there, and how we can more or less easily shield us not only from a Wi-Fi jammer, but also my DIY circuits. Let's get started! This video is sponsored by Würth Elektronik, who provided not only all the shielding material shown in this video, but also this amazing book about the basics of shielding, which comes with some very lovely practical examples, like your tower PC housing. If you want to check it out, then follow my link in the video description. Now when it comes to shielding materials, then it seems like there are 3 big types which get used in almost all cases. And these are different kinds of absorber sheets. We got some shielding cabinets, which I can even form by myself with this DIY version. And we got some aluminium and copper tape. These are really all the essentials. And as you can see, by putting the big DIY shielding cabinet sheet between the jammer and laptop, we apparently already stopped enough radiation, because the internet works just fine again. But of course, using this laptop's internet connection is not the proper way for measuring the effectiveness of shielding materials. For that, Würth Elektronik also sent me these 2 circuits, along with a near-field probe. One is a noise source and one is a near-field scanner. And you can see what they can do after putting it all together and powering everything up. Now as you can hear and see, the receiver is not happy about the noise source. The reason is that it is using this 40 MHz oscillator here to obviously create a 40 MHz waveform that gets radiated through the square antenna. The near-field probe picks this radiation up, which then gets amplified and turned into DC voltage, according to which the LEDs and buzzer reacts. So basically, the more radiation the probe reaches, the bigger the DC voltage, and thus the more LEDs light up, telling us that this is bad. And yeah, this seems to work pretty well as a basic demo, which shows us that pretty much any of the given shielding material does dampen the radiation. And of course, some perform better than others, mostly because of their thickness or their material choice. There are only 2 problems. The first one is that this setup is limited by the used amplifier, which caps out at a max of 1 GHz, meaning my 2.4 GHz jammer is not a great fit for testing. And the second one is that this scanner only judges about the overall strength of the radiation, and thus we cannot tell what frequencies are the big problem. Which is really important though, because when looking at the shielding material data, there's always some kind of diagram involving frequency. So I pushed away this simple yet lovely demo and got myself this thing here, which is an SDR, aka software defined radio. its max range goes up to suitable 6 GHz, and thus by simply attaching antennas to its inputs, connecting it all to a computer and using a fitting software, we can see exactly what radiations with what frequencies are all around us. So when we position this setup next to our jammer, then we can see that while being powered off, the radiation looks like this, and when turning it on, it looks like this. Oh boy! Now when putting any of the shielding material between jammer and SDR, then it does decrease the radiation that reaches it, but not in a big way. To show you the best way though, let me firstly insulate my circuit with electrical tape so that nothing will short out. Then I put the jammer onto a copper board, onto which I soldered a shielding cabinet, which I then completely sealed shut with additional copper tape. And bada boom bada bang, we got a Faraday cage, out of which only very little radiation should leak, which was definitely proved by the SDR. I mean, just compare the before and after measurements. The funny thing is though, that in such a case you don't need all this specialized material. I mean, simply get yourself some tinfoil, wrap it around the jammer so that there are absolutely no gaps, and you will get some pretty similar good results. This way even my internet connection works just fine besides this active jammer. So in conclusion, the material choice does not really matter here, as long as the jammer is completely encapsulated in conductive material. But why is that? Well, when we have shielding material, then the majority of the waves that hit it either get reflected or absorbed. Now when dealing with higher frequency far fields of above 2 MHz, which our Wi-Fi jammer definitely is, then 99% of the radiation will get reflected, meaning the choice of material does not play a major role, as long as it is conductive. Far more important in this case is that there are no gaps, because the wavelength of our jammer waves is rather small with 12.5 cm. That means that with just a 2 mm gap, the shielding effectiveness could be limited to 20 dB, which is like 100 times less power coming through, but that can still cause problems. So now you know why your ESP microcontrollers all come with such a cabinet, and how easy it actually is to shield from a Wi-Fi signal. But now let's move over to my DIY buck boost converter, whose main switching IC uses a frequency of 2.4 MHz. Sadly, my SDR cannot go that low, but luckily for us, we also got problems in this 100 MHz to 200 MHz region created by the harmonics of my converter. So let's hook it up to a constant load, power my converter so that we get a stable output voltage, and then bring the SDR closer. After adjusting its main frequency to 150 MHz, we cannot really see any kind of interferences yet. But as soon as we draw 500 mA from the converter, they quickly appeared. And in case you're wondering, these hills are our harmonics, which are all 2.4 MHz apart from one another. So as a first test, let's once again insulate the circuit, and then try tinfoil once again, which certainly damped the radiation a bit, but not as successful as before. The shielding cabinets with copper plates and copper tape did a slightly better job, but not by a lot. The reason is that lower frequency magnetic field waves do not get reflected that much, and instead need to get absorbed. So as a crude last attempt, I simply slapped a bunch of the absorber sheets onto my setup. And guess what? That damped the radiation so much that you can only barely see the hills anymore. Lovely! This worked because absorption mainly depends on the thickness of the material as well as its permeability, which consists of mu line and mu line, and those can be found in all the diagrams here. The first one describes how well the material can redirect the magnetic fields, while the second one is the ability of the material to absorb the magnetic fields. And as a bonus fact, this can be really useful for NFC or RFID, since you can redirect the required waves while damping unwanted frequencies. But getting back to topic and our final conclusion, which we can summarize in a rule of thumb that says that when dealing with higher frequencies, basically anything conductive and enclosed can do the job. And when working with lower frequencies, you need something thick with fitting permeability. And don't forget to slap on copper tape everywhere, because this is like duct tape for EMC problems. Now of course, EMC shielding is a big rabbit hole that you can get lost in, but I hope with this video I could give you a small overview of the most important things. So thanks for watching, and I hope you learned something new. If so, don't forget to like, share, subscribe and hit the notification bell. Stay creative, and I will see you next time!